the recording. There we go. Welcome everyone. My name is Wes Hines. I'm the Nuclear Engineering Department head here at the University of Tennessee. Today we're going to have a special colloquium. Usually we have our colloquiums on Wednesdays from 1:30 to 2:30, but we were all squeezed up with colloquiums and we had an opportunity to hear from a bright young scientist and wanted to take advantage of that, so we scheduled an extra colloquium or seminar today. Oops. So I will go ahead and introduce Livia. Dr. Livia Casali is a staff scientist in the field of nuclear fusion research at General Atomics. She's the leader of the core edge integration area for the D3D tokamak in San Diego. Her work is focused on core edge integration solutions with special emphasis on the role of radiative divertor and impurity behavior to achieve performance operating scenarios with mitigated heat power loads, which are essential for future fusion reactors. She works on both experiments and computational modeling. She has led the first impurity seeding experiments in the newly installed slot divertor at D3D, investigating the new findings with cutting-edge diagnostics and state-of-the-art computational tools. Her research has been highlighted by the U.S. Department of Energy and featured in journal papers. She was also awarded the D3D Science Director Special Prize for an exceptional invited talk at the American Physics Society Conference in 2019. She studied nuclear and subnuclear physics at the University of Rome in Italy and at the Albert Ludwig University of Friedberg, Germany. With the fellowship awarded by the German Academy Exchange, she performed her master's thesis at the Max Planck Institute for Plasma Physics in Garching. She received her PhD from the Max Planck Institute for Plasma Physics in Garching and the Ludwig Maximilian University of Munich. For her PhD work, she was awarded the EPS PPCF. Livia, I don't really know what that is, but that prize at the European Physics Conference in Berlin in 2014. From the Italian Physics Society, she received the award for highly proficient scientific activity entitled to Pietro Blaserna, the founder of the Italian Physics Society. Welcome, Livia.
Oh, thank you. That was an amazing introduction. I actually prepared a slide about, but maybe I can I can skip my introductory slide. Thank you so much for this nice introduction. And it is my pleasure to be here today and have the opportunity to show you some of the work I've done in the field of nuclear fusion. I'm going to share my screen. Just give me a second and I'm gonna do that. Okay, can you see the PDF?
Yes.
And try to go in full screen. Okay, can you see this?
Looks perfect.
All right, okay. So yeah, I'm gonna show you some of the work I have done, especially try to address this core edge integration challenge in magnetic confined fusion devices. So all right, well, I guess I'm gonna go quickly here. So my name is Livia Casali and I come from Rome, Italy. And growing up, I had two passions. One was physics. I really like to find kind of answers to a lot of questions I had. And the other one was I wanted to become a ballet dancer. The reason I'm saying this is because I know there are some students listening to this, and I think these are really positive experience to share. So eventually I did that for some time. I have been professional in Rome. And the main point here is that many skills that I actually learned from that days are very useful for my career in science. Not only like a teaching experience, but really like other skills like commitment, teamwork, creativity. These are all skills that became really useful. So I studied nuclear and subnuclear physics at the University of Rome and the University of Freiburg with a master's thesis at the Max Planck Institute for Plasma Physics, where I stayed for my PhD. During my PhD, I had the opportunity to complete the International Helmholtz Graduate School and the European Doctoral Network in Fusion Science and Engineer. And this was really a nice opportunity to travel around Europe and meet a lot of students from different countries and different facilities. So if people have the opportunity of doing this kind of experiences, I really recommend to do so. Then I came to the United States with a postdoc to work at General Atomics. So I'm a staff scientist at General Atomics. I am the core edge integration area leader for the D3D tokamak program. D3D tokamak is the largest and the only, as right now, the currently only operating in the United States. It is really a multi-institutional research team, more than 700 user scientists. So it's really an amazing place to be. I'm also an expert member of the International Tokamak Physics Activity Working Group. And what do? I design, execute experiments, as well as performing computational modeling with a variety of different codes, with the goal to develop and understand how to mitigate the interaction of a hot core with a cold edge and achieve operational scenarios for future reactors. I'm happy to say that my colleagues are truly around the world. I work with the people affiliated with the different international institutions around the world. And here I just put some, the logo of some of these different institutions. This is really one of the benefits in working in a field like this. So as you might know, or you might not, 35 nations are working together to build the world's largest tokamak. This is called ITER, in Latin means the way, is truly one of the most ambitious energy projects in the world today. So the most complex machine ever conceived is today under construction in the south of France, as I'm showing from this picture here, with the goal to prove the feasibility of fusion as a larger scale and carbon-free energy source. So to me, this is just really fascinating. What motivates me to wake up every day and go to work knowing that we are doing something for addressing climate change and the energy problem. For my seminar, I'm going to introduce tokamak research. I will talk about radiative cooling, impurity transport study, and detached divertor, on which I dedicate a lot of my career and are really kind of outstanding issues as right now in tokamak research, which will lead me to also present this core edge integration challenge. I will conclude and then I will have some final remarks. So in order to achieve a fusion, we need a high temperature because we need to enable the particles to come close together to overcome the Coulomb barrier. And such high temperature must be maintained for a sufficient confinement time with a sufficient ion density in order to obtain a net yield of energy. So we identify a figure of merit for fusion performance, which is the product of NT tau, where tau is this energy confinement time. And the way that we confine the plasma is through the tokamak concept. So this donut here, we use external magnetic field coils to produce a toroidal magnetic field. And then a plasma current is induced by the central solenoid. And then the superposition of both the toroidal and the poloidal magnetic field creates these helical structures on which the magnetic field lines wind themselves around the torus. This is a cross-section of the plasma. So we heat in the center, but then the heat and particles diffuse towards the edge. They cross at the separatrix, which is this blue line, is the last closed surface. And then the hidden particle follow the magnetic field lines here in red, that now they are open to reach the divertor region, which is the main region of the plasma exhaust. Now, in future reactors, if we do not mitigate these fluxes, these are going to be above 300 megawatt per square meter. However, we have some material limit that tells us that the diverter target load should be below 10 megawatt per square meter. And also we need to keep the temperature at the target below 5 eV to suppress erosion. So here you realize the kind of challenge that we have had. And this is telling us two things. One thing is that material research is crucial. And in fact, UTK is doing a lot of interesting work through research group of Professor Donovan and Vert and Zenko. So I'm not going to talk about that. What I'm going to talk about is the other thing that this challenge is telling us, that we need to increase power dissipation to more than 95%. How can we reduce diverter power loads to match this limit before they actually arrive to the diverter? One way is through radiative cooling by impurity seeding. So we inject low and medium Z impurities into the plasma in order to convert the power flux into radiation, so we can redistribute it through the whole vessel surface. And the question here is, how do I choose which is the right seeded impurity if I want to radiate in a specific region of the plasma? And the answer comes from atomic data. I'm showing here the radiative efficiency for an impurity as a function of TE. As we can see, carbon and nitrogen have their maximum at low temperatures, and then they are fully ionized. So they are good edge and diverter radiators. Whereas argon and krypton, they still significantly radiate higher temperatures, so they are a good candidate for mantle radiation. In future reactors, we will need maximum diverter radiation and strong mantle radiation. If I expanded this plot that I just showed you to higher Z impurities, you can see that tungsten is up here as its force maximum around 1 kV. So is radiating in the core where we don't want radiation because we are trying to make fusion there. So if we do that, this is going to reduce the fusion gain. This leads to a severe restriction of its concentration into the plasma. And that's a very outstanding issue for machines with tungsten wall, such as ASDEX Upgrade and either in future reactor, which are supposed to have metal walls. So you see here that the understanding and the prediction of the effect of the impurities on the plasma is crucial. I'm going to show you some radiative cooling studies we have performed in ASDEX Upgrade tokamak. ASDEX Upgrade tokamak is located in Germany. It's a very relevant tokamak because it has a magnetic geometry similar to ITER. It is the first device with a full tungsten environment exactly to address the problem of tungsten and study what will happen for reactors. And also back in the days, they discovered the H mode. The H mode is the operational scenario that we use normally today. And practically what they found out is that if they add additional heating power, the plasma would spontaneously transit from an L mode scenario to an H mode. So there is a formation here of this transport barrier, which allows the plasma to reach higher plasma temperature. And this region where we have this steep gradient is called pedestal. And as we are gonna see during this presentation, it really has an important role. This part outside here is called scrape-off layer and the divertor, and is the region with the open fill lines. So we did experiments where we inject nitrogen into the plasma. As you can see from this tomography reconstruction, nitrogen radiates very strongly in the diverter as we expected from the radiative efficiency. And what we could see, this is a time trace of the experiment. The radiation increases when we put nitrogen, but surprisingly, the plasma store energy was increasing. So we really wanted to understand the effect of the radiation on the energy transport. And I went and did this transport simulation with the transcode. We have power balance included or not including the radiation. We could show that indeed the flux of the radiation is located at the edge and not in the core, which is good. It means it's not affecting the confinement in any negative way. And also if we look at the transport coefficient, so the chi, which relates the fluxes with the gradients in the heat transport equation, we could see that the chi wasn't changing. So the core transport wasn't changing while we will radiate with nitrogen, which was the good news. So we were not affecting the core. Eventually, it was found out that this confinement improvement is due to a pedestal effect, which then propagates to the core via stiffness. We also did experiments injecting simultaneously nitrogen and krypton. And this is because, as I told you, we need also mantle radiation in addition to divertor radiation. And you can see clearly this here. We have nitrogen in the divertor and krypton is radiating in a ring around the separatrix. Now, when we add the krypton, we first could still see a little bit to this confinement increase, but then at a certain point, we decided to inject more krypton and we end up with a very localized central radiation and we lose the discharge. So this experiment was actually very important because we could assess which was the krypton concentration, the maximum one we could allow in the plasma before to lose the discharge. So you see here the delicate balance between wanting to have this radiation because we need to radiate, but on the same time, we need to be careful with whatever radiation is going to be inside this last close surface. So it's very, very delicate. While we were doing these studies, it became clear that there was another effect that we really needed to take into account, and this is called non-coronal effect. So impurities enter the plasma as neutrals, and then they are subsequently ionized. If we neglect the plasma transport, there is a balance between ionization and recombination that depends only on TE, as in the solar corona, which is why it's called coronal equilibrium. And this situation occurs in the plasma core. In this case, LZ is simply a function of T. However, at the plasma edge, we cannot neglect the plasma transport because, as I show you here, at the very edge, we have these very steep gradients, and we also have the ELMs. ELMs are edge localized instability, and they have the characteristic of, for instance, reducing the confinement and each crash. And so because of these things, we cannot neglect the radial transport, but then LZ is not only a function of TE at this point, but is a function of NT tau, where tau is the residence time for an impurity. In order to take into account this effect, we went on and did a very detailed study with actually coupling the Astra transport code, which advanced the background profiles of the plasma, with the impurity transport code, STRAL. This was done for the first time, and we were able to study the self-interplay of the background plasma, the impurity transport, and the ELM effects. And the results are showing here. So I'm showing nitrogen for on the left and tungsten on the right. These are all radiation time traces at the very edge region here in the pedestal, and the different colors are just the different radial position in this region. In dash coronal approximation, and in solid the actual result of the code. So we can see that for nitrogen, the radiation given by the code is between 2 and 5 higher than corona, depending on where the location is, showing that these effects are important. However, in the case of the high Z impurities, we cannot really see a difference between the solid and the dashed line, and that's because tungsten has a very high charge. So, and the ionization and the recombination rate, they scale with the Z to the second and to the third. So tungsten reaches the equilibrium really fast. And these effects then are not important. And this is very important in order to extrapolate eventually to reactor. These radiation enhancement I show you with nitrogen can be understood if we look at the ionization profile. I'm showing here the fractional abundance of nitrogen, and we can see if we look at shell number 6, for instance, clearly what's the effect of this transport is the broadening of the shell, such that now the shell is at higher temperature than it would be in a normal equilibrium, so it's radiating more. And this is what is so-called non-coronal radiation, and is very important in order to not underestimate the radiation, especially at the plasma edge. We did another study which was to test what happens when we change the frequency of these instabilities at the edge of the elms. So these elms have a lot of effects, mostly bad, but they do one good thing, and is that they actually flush out impurities from the confined region outside to the open field line, so that we avoid this impurity accumulation that then lead to the central radiation I just showed you. So we wanted to test what would happen if we change this frequency. And so here is the result. For nitrogen, we did not see much difference if we would go from 140 Hertz to 10 Hertz. However, when we change this frequency, keeping the energy loss constant for tungsten, this radiation was increasing to a factor of 4, till a certain point, there is a crash here. So the simulation crashed because there is too much radiation. This different behavior between nitrogen and tungsten can be explained, so again, in terms of this high charge, because the profile peaking increases with Z. So for tungsten, this is very important. Tungsten develops very quickly a high density profile related with the high radiation. So the radiation becomes higher than all the heating powers, and the simulation crash through collapse by radiation. And this was actually really important because back in 2011, it was already seen experimentally that an F elm, so a frequency of the elm of 10 Hertz at least, was required to not lose the discharge. And now, doing all the simulation work, putting in there the physics of the impurities, of the elms, of the plasma, we could actually show that indeed we needed at least 10 Hertz to sustain the discharge. So this really showed the importance of having this high Helm frequency in this scenario to control tungsten in the confined region. If we go back to the main question, how we reduce the divertor power loads to match the technological limit. The other thing that we need to do is to work with a detached divertor. Detached divertor means a cold dissipative divertor where the heat and particle flux at the target are reduced. So it means that we will need to go from this black case to this red and violet case. The physics mechanism is the following. So as you remember, I told you like the hidden particles are, they cross the separatrix, and then following the magnetic field line, they go towards the divertor. So till they meet the impurity radiation zone, which is around 10 eV. Here, intrinsic carbon from a carbon machine or extrinsic nitrogen, as I just showed you in the examples I presented, they radiate strongly. This is the main drive of power exhaust in tokamaks. This radiation through impurity seeding enables the plasma to drop the temperatures to around 5 eV, where the ion and neutral interaction zone is found. So now charge exchange, elastic collision, they all start to play a role, and they are able to drop the temperature to around 1 eV, where the recombination zone is found and the divertor is finally detached. The physics is extremely complex, which is why I like to show this, figure here, just to give an idea of all the processes that are happening: ionization, dissociation, the recycling atoms, and molecular recombination. So that's why we need to use coupled fluid and kinetic code to actually pin down the physics. I'm going to show some of the detachment study in the D3D tokamak. D3D tokamak is the US National Fusion Facility, is operated by General Atomics in San Diego. As I mentioned earlier, over 700 user scientists from more than 90 institutions. This is the inside of the tokamak. This pre-COVID was an ordinary day running the machine and doing experiments in the control room. Usually is a lot of fun, and if you are actually running the experiments, you are supposed to bring donuts. And so we would also eat a lot of donuts. Hopefully we can come back to that eventually. But so it's a very, very dynamic environment, and it's really a nice experience to be there. So it has been shown in a number of tokamaks that the detachment onset is influenced by divertor configurations through variation in the baffle geometry. In the 90s already, Alcator-Simode, which was the machine run by MIT Boston, showed the importance of closing the divertor to achieve better detachment. So D3D went on this line of studies, and today we have three different divertors. We have an open divertor, we have a closed upper divertor, and then we have a small angle slot, as I'm showing here, which is characterized by high closure and target shaping. Experiments at D3D have showed that the upper close and the slot diverter can detach a lower upstream density than the open diverter, which is a good news for the core edge integration. So, of course, the question is why? What are the processes that are responsible for detachment, a lower upstream density? And that's why we need to use these codes I was mentioning before. The most important code for doing this difficult job is called SOLPS, a scrape-off layer plasma solver. It's a very complex code. It's the coupling of B25, a multi-fluid plasma code, which provides the plasma background on which the neutral trajectories are calculated by the IRENE Monte Carlo code. And then IRENE gives the sources and the sinks due to neutrals back to the fluid plasma. The results of the modeling of the experiments are shown here. We can see that indeed the closed diverter in blue can achieve lower TE and lower heat fluxes than the open diverter, and this lower value can be also achieved at lower density. When we started to do this systematic work on diverter closure, we find out that we first really needed to define what diverter closure was for us. Diverter closure has been, this kind of concept has been around for a long time, but it has been kind of elusive. I think that the best way to show this is actually to show these Monte Carlo trajectories of neutrals. You can clearly see in this case that the neutrals accumulate at the target in the closed diverter, whereas in the open diverter, they kind of scatter everywhere. And so we don't really have a neutral trapping. So in this work, we define a diverter leakage parameter, which is pretty much the ratio of the neutrals that escape the diverter through the ratio of the neutrals that are born in the diverter. And with this, we could quantify that the neutral escape, the percentage of the neutral escape in the diverter at the detachment onset was 12% for a closed diverter and 35% for the open diverter. One of the reasons for this is an increase power dissipation in the diverter. Here I'm showing the open diverter on the left and the closed diverter on the right, and you can see in black P net, so the power loss is higher in the closed diverter compared to the open diverter. And the code actually is also enabling us to break out the single contribution to the radiation. So if we look in more detail, we can actually learn that the reason why this power loss is higher in the closed diverter is because the neutral radiation and the neutral interaction constituents are higher in the closed diverter, and that's happening because of this neutral trapping I just showed you in the previous slide. But that's not the end of the story. There is another piece. Here I'm showing the open diverter on the top and the closed diverter on the bottom. This is the heat flux to the target. In green, the convective flux, and in magenta, the conductive flux. So as you can see in the closed geometry, there is pretty much not convective flux except right here, the target. And that's because the particles cannot escape. They are trapped in the diverter, so there is no particle flow. But then the heat must be carried by conduction. So the heat is carried by conduction. You can see here in magenta, which however have a very strong temperature dependence, as you can see from the equation. So now if I go and I consider the expression for the upstream density, this is given by this two-point model. You can see that in this equation, the radiation fraction enters the equation, the convective fluxes enter the equation. So if I go and I solve this equation for the two geometry with all the values I get from the code, I end up with a ratio of 2.5, which is very consistent with the very first plot I show you of the difference in detachment for the upstream density between the two geometry. And that's a good news for the core edge integration. So this core edge integration is now one of the greatest challenge in tokamak. It's about really integrating the hot core and the cool edge. And as you could see, the physics is very different. And there is a fundamental tension between a diverter solution, which favors a high density. Also, diverter closure can help with this, as we just saw, and the core solution and the current drive that in fact require low collisionality. In particular, if we wanna work in steady state in future reactor, we need to have a low density fraction. So how can we improve this integration? This, of course, requires a broad understanding of all these underlying physics process. So in my case, I've used the experience I gained in core transport, pedestrian transport, and in diverter physics, and try to contribute to this challenge. So here was the idea: what if we combine a diverter closed geometry with target shaping and impurity seeding, and we try to improve this core edge integration? So this has led to a very comprehensive work on the effect of diverter geometry and radiative species. in the newly installed SAS slot diverter D3D. This has been also enabled by important advancement in computational modeling and unprecedented diagnostic coverage in a closed diverter. This work has been highlighted by the Department of Energy. And if you want to read about this in a less technical way than what I'm going to show you in the next few slides, then you can read this article. So impurity seeding studies in this small angle slot, the SAS is located up here, and this is the how it looks like. And as a lot of diagnostics, as I show you, and I would like to highlight that the eroding thermocouples have actually been designed, installed, and operated by David Donovan and June Rain from University of Tennessee. So this is a very nice collaboration that UTK has on D3D. So when I designed this experiment, the goal was to try to obtain detachment with good core performance. And these were the results. We inject nitrogen into the plasma, and we really observed the first simultaneous observation on detachment on all the boundary diagnostics that were looking at the slot. This was happening for the first time when we inject nitrogen. You can see, for instance, this really big increase in the pressure in the slot, so meaning detachment conditions and very cold temperatures. And at the same time, the confinement stays constant even when we puff much higher level of nitrogen. So this was a very important result. Then we wanted to study the effect of the divertor geometry. And so what we did is that we were changing the strike point from the inner surface to the outer corner of the slot. And what we found for all the database that we collect was that when we had the strike point in this position, we could see higher core impurity concentrations into the core. But not only, for these matched discharges, we could also see that we needed high nitrogen path for the temperatures to drop in the diverter and for JSET to roll over, where JSET is the particle flux, and this rollover that I'm showing here also is a sign of detachment. So we needed more nitrogen for some reasons for this configuration here. So then, in order to interpret this very interesting results, I went on and started this SOPS either modeling with the full particle drifts and multiple impurities included. This has been performed here for the first time. And particle drifts are induced by electric field in the diverter. And they are actually pretty important, which is one of the main takeaway, although historically has been hard to take them into account because they made the simulation very heavy and very unstable. But anyway, we went on, we were able to show that drifts are necessary to interpret the experiments here. And you can see what is the effect of this. This is the ionization distribution of deuterium, and these drifts are shifting particles from the outer diverter to the inner diverter. But not only the ionization distribution is affected by drift, is also affected by the magnetic configuration, the geometry configuration. So if I change the strike point from this inner surface to this outer point, also I see a different distribution. And that's because different strike points corresponded to different wetted area with a different distribution of the ionization source itself. And this is very important. And the reason is because the divertor geometry influences the plasma flow via modification of the ionization source and has tremendous consequences on the impurity transport. A flow reversal, a flow away from the divertor, occurs in a flux tube where the ionization source exceeds the ion loss. You can see this effect here in this orange and green region. In this case, the power is being now convected away from the diverter. And these kind of effects are entering the impurity transport equations. Now, we don't have to go in detail all the equations, but what you need to know is that the impurity velocity, which gives me the transport, is determined by the velocity of the main ion, the gradients of the temperatures, and these particle drifts I have been talking about. So all these effects are entering the impurity transport equation. And so if I go and I plot these flows for my case, and I have the main ion flow on the top and the nitrogen flow on the bottom, we can see that we find these regions with flow reversal. But if the strike point is at this inner surface rather than this outer corner, there is less of this effect. The nitrogen is better retained in the diverter, and this could explain the experimental observation of why, in this case, at the inner strike point, we could see less nitrogen in the core, and why we needed also less nitrogen for detachment. So this was really kind of a big, important step to advance our understanding of the impurity transport and how the scrape-off layer transport is really affecting now what is happening inside the confined region. Now, while nitrogen is a good diverter radiator in present machines, as I show you through this presentation, the choice of the radiative species is important. So nitrogen is problematic for future reactors due to ammonia formation. And so especially ITER is really looking into neon, and they want to know if neon works as well. As you see, neon in the radiative efficiency plot is somewhat in between nitrogen and argon. So what we did is that we did these experiments and now try to match neon with nitrogen, of course, taking into account this different radiative efficiency. And what we could see is that neon increased the radiation in the core, as we expected from the different efficiency. And so it's like that, you know, nitrogen radiates here in the diverter and neon more up here. This is also confirmed by the modeling again. As you can see, nitrogen in here in yellow is very well trapped in the diverter, which corresponds to this blue color. So regions of very cold temperatures, whereas neon penetrates more upstream. And this dissipation upstream can be also seen by this plot, where now I'm plotting the heat flux at the diverter entrance. So before we are entering the diverter, okay? So right here. And as you can see, this Q parallel in the case of neon is already reduced because neon is operating here. Instead with nitrogen, nitrogen is operating in the diverter, and the flux down at the diverter will be reduced, but not at the diverter entrance. So if we take that equation that I show you already about the upstream density, well, this equation is now linking the diverter and the pedestal through the heat flux and through radiation. In the case of neon, neon is reducing both these terms, the radiation through this mantle radiation and Q parallel, as I just showed you in the previous slide. But then this means, and this has an important implication, that for a given temperature at the target, we would need less scrape-off layer density. in the case of neon. And this indeed is verified if we plot the profiles. So in green, we can see this less scrape of layer density. But also we see that we can actually reach an increase in the pressure gradient with the neon. To conclude this part, I show you that we have been working on this core edge integrated scenario for the 3D, demonstrated the compatibility of an edge solution with good core performance. And what we can do for that is to choose radiative species, which are good for the pedestal conditions that we want to achieve. We can work on the divertor geometry, even just changing the strike point in the slot leads to very different situations. And also we can tailor the drift for entrainment through the geometry. To summarize, I show you that impurity seeding and divertor detachment are essential for core edge integration. Impurity seeding is crucial for power exhaust, but it can also help and even improve the confinement. However, the central radiation must be controlled to avoid impurity accumulation and collapse by radiation. Non-coronal equilibrium is important for Lysid impurities, but not for IZ. Divertor closure, important to obtain detachment and lower upstream density, so more compatible with the core. And this is happening because of higher radiation changes in power balance. A core edge integrated scenario was developed by combining the SAS divertor with impurity seeding and advancement in state-of-the-art simulation tools, including particle drift and multiple impurity species, have been able to explain the experimental results. Future for the core edge, one thing I actually just started working on this upgrade of the gas system at D3D, which will enable more innovative gas injection strategies. As you saw through the presentation, is important where we inject, how we inject. So this should be important for better improvement of the control of the radiation. We are also working on a new proposal for divertor upgrades. We just had a workshop last week. Continue and expand work on the core edge integration also to other international facility, especially in the UK and in Switzerland. Of course, to continue the work to support ITER and eventually towards the US XI facility that has been proposed by FISAC, right, to address this core edge integration. In 2018, DOE had requested a strategic planning activity to advance the development of fusion as an energy source. And this has led to a tremendous community workshop that led to the release just recently of a community report and the strategic plan. So this is really an exciting time for fusion research. And last but not least, I believe that engaging students, general public, decision makers is key to make a fusion as energy source a reality. So in addition to my scientific research, I dedicate time to engage students, to simulate women in science. Here I'm showing a picture where I serve as a panelist at the American Physics Society Conference for Undergraduate Women. We also organize a Plasma Expo and hands-on workshops. And also I'm honored to say that together with other few people, we have the possibility to advocate for fusion energy at the US Congress and the Senate. This is a very important opportunity to explain them what fusion is, why it's important, and why we need more fundings. And so this picture was actually taken exactly 1 year ago on this day, right before COVID came. And but this is the time of the year again. So in fact, next week on March 4, we have this appointment. This time is going to be virtual, but we will have a lot of good news to tell them because of all these reports I just mentioned. So if you want to get engaged in fusion or you want to know more, feel free to contact me. And with this, I would like to thank you for your attention, and I'm happy to take any questions.
Great. Thank you, Dr. Casali. We have time for questions. If you have a question, I think if you just raise your hand, you'll pop up to the top of my list, and I should be able to allow you to speak. So I don't see any questions yet. So
I have my hand raised. But
oh, you do? Okay, sorry.
no,
Go ahead, Sean.
Okay. Yeah, thanks for the talk. I wanted to ask about where you showed your more recent results with the drifts through the private flux zone. I was wondering if you have any sort of, because as you know, the drifts will depend on the strength of the, I guess in this case, the radial electric field. I was just curious how confident you are in your values of that, like if you have any kind of experimental constraints on what the expected drift strength would be in the private flux zone.
Let me get back on this slide. So let me see here. So this is going to be one of the kind of next step that we can actually, compare the flows with some of the measurements. However, the modeling has been constrained with experimental values, and we could reproduce many aspects of of the detachment physics. In the measurements for the flow itself, this needs to be done with the flow measurements. And as you know, there is a lot of work now that has been done in terms of measurements for the flow, specifically in the open diverter. But we are, I would say, confident because we are actually constraining a lot of physics already through matching the experimental profiles.
Okay, thanks.
Okay, Dr. Donovan?
Yeah, so definitely excellent presentation. I think I'm going to want to borrow some of the slides to explain diverter attachment. You have some really good figures showing the modeling and the theory, really excellent combination. I guess in terms of the experiments you've highlighted, things like TCV and MASS and other devices, I guess what is your kind of thoughts on how do you rank choosing a collaborating institution in terms of their ability to have a diverter geometry or impurity injection capabilities or diagnostics? Obviously, it's kind of always a combination of all of these, but how do you prioritize? What do you look for an experiment?
Well, so I mentioned specifically these two because these two facilities, and you probably are aware, are actually really working in this direction. So TCV, and I have been kind of in contact with them, especially recently. They have started to do a lot of work on this diverter closure. They installed new baffle like just a couple of years ago. They have actually show a lot of results during the PSI, and these results are very in line with what actually we saw at D3D. So for me, it was very, very exciting to see the result coming up. So they just did their own force experiments, and they will continue to do so. They have a very flexible capability of reaching more different diverter geometries, which for me, this is very interesting. And so that would be, one of the priority, definitely, a machine that has new baffled and new capability for changing diverter. This is definitely very interesting. The other one is MAST. MAST-U is, coming coming up to speed. It has an amazing diverter capability, a lot of also capability for gas path valves. So this is, to me, also really looking at the future. It will take some time before, I guess, we will able to really go and do the impurity seeding experiments like this way. It will take some time, but they will get there. And so that there I see a very good opportunity with the specific diverter that they have and all the capability with the gases. So balancing the two, leveraging the two possibility, I think these are really good places where we can keep on improving this kind of physics. And then, of course, you know, D3D, we just had this workshop last week, and you know, hopefully we go ahead and we will be able to do some upgrades and the upgrade. So the upgrade of the gas system is going to happen because apparently that's kind of my job for for the future, to upgrade this gas system. So I guess that's going to happen no matter what. And for the diverter, well, hopefully we will able to, you know, kind of find a plan for a new diverter upgrade. So.
Okay, it looks like we have, oh, sorry, David.
I was just saying thanks.
Yeah, so we have 4 hands that came up, so we're going to give rapid fire questions, I guess. So we'll start off with Yajendra, and then we can go to Dr. Zinkel, and I kind of know who raised their hands first.
I'm still kind of phrasing my question, so I wouldn't mind if Dr. Zinkel asks first.
Okay, Dr. Zinkel.
Okay. Hi. Thanks for a great talk. I was just wondering, from a edge physics perspective, how far along are we towards understanding how to optimize for like a tungsten diverter versus a carbon, you know, historic carbon graphite diverter, etc. Do we understand the edge physics pretty well, or are we still in a steep learning curve? Just kind of as a general perspective from your experience.
This is an excellent question. And, you know, like I think, so the good part for me is that I had experience on both tungsten machine in ASDEX and now a D3D with the carbon machine. And the real truth is that, you know, we will have to work with tungsten because that's what is going to be. The diverter will not made with carbon, and the tungsten as you know, as his own issue, right? Like whenever ASDEX transit from having a carbon wall to the tungsten wall, there were a lot of facts that we were seeing. And the first was this confinement degradation. The confinement was really decreasing when the machine transit from carbon to tungsten, which is why it was so important to see that injecting nitrogen, we were actually able to bring back the confinement to whatever there was with carbon. Carbon allows more flexibility in terms of operational scenario configuration. A lot of core scenarios are just easier with tungsten. But I think that by now, also with JET that has been operated with, you know, tungsten wall for some time, I think the physics of the tungsten is actually pretty clear. I mean, mainly the edge is governed by the neoclassical transport, and neoclassical transport scale as a Z. So that all the effects I show in the first part of the talk, this impurity accumulation and central radiation, are all linked to the fact that tungsten has a high charge state. But we are also developing a lot of tools to, you know, control these radiations and all these effects. So I think the physics is well understood. What needs to be more understood, in my opinion, is really this link between the open field region and the confined region. And that's what I was trying to see in the very last part of the talk. Whatever happened in the scrape-off layer, that all this reversal and this impurity transport that happens there actually is a great business for the confined region, because if the flow reverse, then all these impurities now are going to be in the confined region, and that's something we need to know so we can work on that.
Okay, great. Thank you.
So we're down to 2 questions. We'll see if we can squeeze them back in. We have looks like a researcher from Oak Ridge, Jake Nichols, and then we'll go to Promise.
Hi, Livia. Great talk. Thanks. In your nitrogen and neon seeding experiments, did you see any impurity purging or leakage effects that were correlated with elm frequency or elm size? And I guess more generally, what do you think the best way forward is for modeling these sort of time-dependent plasma regimes, given the very, highly coupled diverter plasma solutions that are already just in our steady state codes?
Yeah, this is a great question. Actually, I do, well, I don't have it here. I try to avoid to go in even further details, but I do have a plot. I can show you how you can see that the neon eventually, so after some time, neon is in the plasma, is reducing the elm frequency, right? And that's where, now in this case, it wasn't a big deal in this 3D, but that would be a big deal for a tungsten wall, for instance. So you can definitely see how the elm is changing the frequency more gradually with neon. And then something that indeed we will have to take into account while, working with the 2 different impurities. But yeah, that's a good question. I can show you some plots about that.
Okay, Promise?
Yeah, thank you so much for the talk. My question is, in your experiments, like, did you see like tungsten and nitrogen diffusing into the core? And I guess to follow up on that, did I guess nitrogen layering in tungsten, does that, I guess, promote that even more? Like the layers that nitrogen forms in tungsten, like, does that cause more erosion of a tungsten diverter?
Are you speaking about the target, or are you speaking about the core? No, sorry.
I guess like because you mentioned like the radiation in the core, so I wanted to know, like, does that get into the core and then layering in the target?
Yeah, so, well, that's where tungsten radiates, right? Tungsten doesn't not radiate in the edge, tungsten radiate in the core. So if it radiates there, I mean, it's pretty bad. So we see all the radiation happening into the core, which is triggered again by the fact of this, what I was just explaining about this neoclassical transport that's scaled with the Z. And that's why we need to be careful and try to control. We can control it through these instabilities, for instance, because that would help to flush out tungsten in the confined region. We did not see specific really increased erosion at the edge, but also this is not something I was personally paying too much attention during the studies because I was working in the core. But if you are interested, I can look into that more in detail, but it must not have been something really that important because I cannot recall there was a big issue. The real issue was the penetration into the core, and then we would lose the discharge. So that's why we worked on estimating the concentration that was allowed through the codes.
Thank you.
Okay, Yujendra, it looks like you jumped back on there, so let me let you slide back in.
Thank you, Professor. It was a really nice talk, Dr. Casali. Thanks for that. I have first I'd like to start with a question that I saw in maybe slide 20, 21 across there. It's just a doubt about the radiation, the power losses, and there was a factor of 4 that you were trying to communicate with 145 hertz. I just quite didn't notice that. And other question was since you said these the drifts are dependent on the target, where are they targeted, and the diverter geometry. So do you see the same kind of trend in mantle with argon and krypton?
So this work with the drift wasn't done with krypton or argon. I mean, in general, you know, it's not that they are dependent on the species. Drifts are in generally, so they arises from electric fields from the gradients. So any kind of particles is gonna you know, follow whatever drifts are enforcing in there. So we see them with nitrogen, we see them with carbon, we see them with neon, with whatever impurities we have there in the moment. So it's not depending on that. What is depending is the magnetic field direction. So if we would have the magnetic field on the other side, then we would see a different pattern for the drifts. But it's like the same for all the particles.
Sorry, I think I didn't do a good job communicating the question, but yeah, I probably will email you about it. But the other thing, like, don't you about the divertor legs, like if we push it away from it, wouldn't it create much more of a problem if we create much more asymmetries? Because if you're like pushing the target to another point, wouldn't it create more asymmetries?
Yeah, it depends. So that's why I mentioned at the very end to work on the drift for particle entrainments. It depends where these particle drifts are going. You know, it depends where are they going. But then you can put a pump, for instance, to part the particles, considering where your flow is going. So if you know what these flows are doing, you can actually actuate on these flows. And that's why it is important that we understand their trajectories so we can put actuators for that.
Okay, thank you.
Okay, we have one last question. I know we've gone over, but I don't want to shortchange anyone. So Kirtan, I think you're one of Dr. Donovan's Bredesen Center students, correct?
Yep, that's correct. Thank you. Thank you for the talk, Dr. Casali. My question was about the divertor leakage parameter. You did measure it with single null configurations, but what if there's double null configurations? How would you prioritize, and how would you know where the leakage was primarily from?
Well, this is a very good question. This is something that we could test. That specifically, this was the most general parameter that we could come of. It's pretty much really like, you know, how many neutrals are escaping through the X point. This is an integral, is the integral of the flux through all the neutrals that are born into the diverter. And so you can do that exercise also for the double null, for instance, and see how many they are coming from the other X point, and then you can compare. That would be a very interesting exercise, in fact. So if you do, let me know.
All right, thank you.
Okay. Well, usually we say, let's all thank Dr. Casali, and we all clap, but no one can hear anybody clap. Livia, thanks so much for taking time out of your day to come speak to us and speak to our students and speak to some of our colleagues out at the lab. Really great talk, and look forward to talking to you more in the future.